Large language models can do some incredible things. They can write poetry, they can debate philosophy, they can even write code. But ask one a simple math problem, and things can get, well, a little weird. So, what is actually going on inside that black box when it sees an equation? Is it really thinking and calculating, or is it just a super clever parrot repeating patterns it's seen thousands of times before? That's the mystery we're going to try and solve today. We're going to go on a little investigative journey. First up, we'll lay out the central paradox, the big puzzle. Then, we'll start hunting for clues. Is it all memorization, or is there real calculation happening? We'll look at the huge breakthrough that completely changed the game, and then we'll peek inside that black box to see what's really going on under the hood. Finally, we'll deliver the verdict and end with a pretty mind-bending twist about where all of this is headed. All right, so let's get right into it. The puzzle that has had researchers scratching their heads is this. How can these incredibly powerful AI models, the ones that seem so brilliant, often stumble on something a $5 calculator can do without breaking a sweat? And this really gets to the heart of the contradiction. You've got models like Google's Minerva that can walk you through step by step the solution to a complex college-level physics problem. But then that same type of model might completely fail at a simple multiplication problem it's never seen before. It just doesn't feel like it makes sense, right? How can you ace the advanced logic but flunk basic arithmetic? This is the core of our mystery. So that paradox leads us right to our first big question, and kind of the most obvious suspect here. Is it all just memorization? I mean, let's really think about that possibility. Is the AI just pulling answers from its massive training data? Like a student who crammed for a test by memorizing the answer key but never actually learned how to solve the problems? And look, the case for memorization is actually pretty strong when you first look at it. These models have basically consumed the internet, which includes countless math problems and their solutions. So yeah, it stands to reason they've just stored away common facts, formulas, and problem structures. Researchers even point out that memorizing things like trigonometric identities is a key part of how they operate. So, case closed? Well, not so fast. This is where the plot really thickens. Researchers put this whole theory to the test. So on the left, you see what happens when they just rephrased a problem. They changed the words, but kept the numbers the same. And look, the model's accuracy, it stays pretty high. But now look at the chart on the right. When they kept the words the same, but changed the numbers, accuracy just tanks. If it was just about memorizing sentences, changing the numbers shouldn't have made such a huge difference. Something else has to be going on. And this is where things get really weird. Researchers found this totally counterintuitive connection. The better a model gets at memorizing, the better it gets at solving new problems it has never seen before. So memorization and actual reasoning ability seem to grow together, hand in hand, which tells us our first simple theory, that it's all just a memory trick, is way too simple. So if it's not just memory, how did these models suddenly get so much better at math? Well, that brings us to a surprisingly simple but totally game-changing technique. It's called chain of thought prompting, or COT for short. And honestly, it's pretty much exactly what it sounds like. Instead of just asking for the final answer, you tell the model, think step by step. You ask it to show its work, just like your high school math teacher made you do. And this tiny shift in how we ask the question had a massive impact on the answers we got back. And here's what that actually looks like. The model starts breaking the problem down. First, it identifies the key pieces of info. Then, it sets up the right formula. And then, it just tackles one calculation at a time, creating this logical chain where each step builds on the last, all the way to the final answer. So what this process is really doing is giving the model a place to think. LLMs don't have a persistent memory like we do. So by writing out each step, the model can look back at its own previous thoughts inside its context window. It's basically using the chat window as a temporary scratch pad, a kind of working memory that it desperately needs for any problem that has more than one step. Okay, so making the model show its work helps. A lot. But that's still just looking at the output, right? What is actually happening inside the model that lets it do those individual steps in the first place? Let's look inside the black box. But, and this is a big but, researchers are quick to warn us that chain of thought isn't some magic wand. It doesn't suddenly give the AI abstract reasoning powers. What it really does is force the model to generate text that looks like reasoning. It's a structural guide, pushing it to follow familiar patterns like step 1, step 2, therefore. It's getting better at mimicking the form of logic, which isn't necessarily the same as true deduction.
But while that's happening on the surface, deep inside the network, something truly incredible is going on. It turns out the model isn't just relying on a giant, clunky lookup table of memorized facts. Researchers have found that during training, the model can develop what they call emergent algorithmic circuits. Now, unlike memorization, which is rigid and inflexible, these circuits are efficient, they can generalize to new numbers, and they're compact, rule-based systems that just form on their own.
And we've got concrete proof of real calculation. For a basic operation like addition, some models actually learn what's known as a Fourier circuit. The easiest way to think about it is like this. Imagine the model maps numbers onto a circle, like a clock face. To add 3, you just rotate the hand 3 spots forward. The model is doing something very similar, just in a way more complex, high-dimensional space. The key is it learns the rule of rotation. That is a genuine mathematical algorithm. It's not just recalling an answer, it's computing it. So, we followed all the clues. We know it's not just memorization, but it's not some pure abstract reasoning either. It's time to put it all together and deliver the verdict on our central mystery. The real answer to our original question, is it a genius calculator or a clever parrot, is that it's a bit of both. And then, something more. LLMs use this hybrid strategy. They lean on memorization for common facts and familiar problem templates. They use these emergent algorithmic circuits like that cool Fourier circuit for core calculations. And they use structured reasoning techniques like chain of thought to glue everything together for the really complex problems. One paper I read summed it up perfectly. It's not one single elegant system. It's a bag of heuristics. Think of it like a toolkit. A collection of tricks, memorized rules, and these emergent algorithms that the model learns how to apply. It's a practical, kind of messy, but surprisingly effective way to solve problems. But of course, just when we think we've got it all figured out, the latest research throws one last curveball at us. A final twist that challenges everything we thought we understood about how AI thinks. Okay, this is absolutely wild. Studies have shown that the step-by-step reasoning we see isn't always causal. A model can generate a completely flawed chain of thought with broken logic and wrong steps, but still somehow land on the correct final answer. And it works the other way, too. It can produce a perfect logical reasoning chain and then spit out the wrong answer. The work it's showing us isn't always the work it's actually doing. A lot of the time, it's just a plausible story it creates after it's already found the answer. And this leads researchers to ask this really profound, almost philosophical question. Right now, we force these AIs to think in human language, squeezing their thoughts through this narrow bottleneck of one word after another. But what if that's actually holding them back? What if true AI reasoning doesn't happen in words at all, but in that incredibly complex, high-dimensional, latent space, that hidden web of connections inside the model itself? So we're left with this fascinating, almost sci-fi possibility. Maybe the step-by-step logic we read is just a shadow, a rough translation of a much deeper, more complex, and frankly, completely alien form of thought that's happening in a space we can't even directly see. The future of AI reasoning might turn out to be something we can't even read.